A lot for the invitation to be here. It's been a really interesting conference. I'm challenged to learn a lot from the really wide cross-section of expertise that there is at this meeting. My talk will be more focused on experiment, as you can see from the opening slide that shows hardware. And what I'd like to cover is experiments happening in my group where we've integrated optical cavities in atom tweezer arrays and are working toward creating something which will be a rather general programmable system to study open quantum dynamics. And I'll talk about experiments we've done on symmetry breaking dynamics in a mesoscopic regime, leading to some ideas for where we want to take this next. And then I'll finish up with sort of a technical update on some new things that we're developing in our setup. The focus of this talk is on cavity quantum electrodynamics. So just to recap quickly, cavity QED system is one where you place quantum emitters inside of a resonator so as to enhance the discussion of those objects, of those emitters, with one mode of the electromagnetic field over the communication with all the other electromagnetic modes. And the cavity QED system is rather flexible in what you could do with it, which I guess accounts for how many papers are written about cavity QED these days. So here's some summary of what a cavity QED system might serve for. One of them is to enhance your ability to detect your quantum system. So with a high finesse cavity, you can efficiently extract the quantum information from some system into the form of light and then send it on to your detector. So that's useful for us for cavity enhanced measurement related to mid-circuit measurements. You can use the information you've gathered also to apply feedback control to a quantum system. That feedback can either be measurement-based, where you really obtain classical information then feed into the quantum system, or it can even be built in autonomously into how the quantum system is constructed. So we have some work on that I will not talk about here. The cavity QED system is also a way to mediate interactions between quantum emitters. So we can orchestrate a situation where the light emitted by one quantum system is rather deterministically absorbed by a second quantum system. And as such, this photon that's exchanged between them is something that mediates a force or an interaction. And then finally, the idea is that the cavity QED system is also nice as an interconversion or a transduction device, which can take information that's stored in a quantum system and turn it into light beams, which can then perhaps be reverse mapped from the light beam into the quantum system. This might be ultimately how we build up modules of quantum devices and quantum computers. Okay, so this is all a very flexible toolkit. We'd like to use it as productively as possible, and in order to do that, I have to position these quantum emitters rather reliably into the cavity system. And in my work recently, we've really gained a lot from the revolution of atom tweezer arrays, which has moved us from sort of this Stone Age approach where you just put in, a billion atoms coming out of some system and sort of, pour it into your cavity, to sort of the modern age where really with digital control you can place atoms exactly where you want and exactly how many atoms you want. And in our experimental setup, we work with rubidium atoms. The experimental setup, just to skip over some details, we produce a cold gas of rubidium. We place it inside of an optical cavity. This optical cavity is built with mirrors that are spaced kind of far apart from one another. And that allows us to position a high numerical aperture objective that looks transversely into that cavity and allows us both to form optical tweezers where we can trap single atoms, and then also to image the atoms in those optical tweezers so we know which tweezers are filled, and we can rearrange and make, at this point, one-dimensional arrangements of atoms inside of our cavity. The cavity is working in the strong coupling regime, albeit just barely. So single atoms are strongly coupled to the photons that resonate inside of this near concentric cavity. And altogether, we end up with a cavity where the mirrors are spaced by about 1 centimeter, and the microscope is looking at the middle, roughly 100 microns inside of this cavity. And within this little 100 micron region, we can arrange our atoms in one dimension along the cavity axis with, basically nanometer precision of where the atoms are located inside of the cavity. And these days we're working with up to maybe 35 or so atoms, and we have ideas for how to build up to a larger number if that turns out to be what's interesting. All right, so now what are we doing with this quantum system? And I want to turn immediately to the idea of phase transitions that are realized in a mesoscopic regime. I mean, obviously you realize this is a mesoscopic object that I've placed inside of the cavity, and now we can think about its dynamics. And we're going to focus in particular on optomechanics. So let me try to describe that with the following cartoon. So we'll think about the motion of an atom along one dimension. So here's an atom. It's located at position 0, and it can just move along this axis. And it moves in response to, let's say, two light fields that are projected onto it. One of these light fields is uniform, so it just comes in this case, actually transversely to where the atom is moving. So the atom sees a constant value electric field all along this line. The other mode of light that it's exposed to is, let's say, a standing wave of light, so where the electric field goes positive and negative. And, of course, how the atom responds to the combination of these electric fields depends on their relative phase. So if the two fields are in phase with one another, then they generate an intensity pattern where there's high intensity to the right of the atom. Is that to the right? Yes, to the right of the atom. And let's say this atom is attracted to high intensity, this atom would now move to the right. So there's a force to the right in case the relative phases of these two beams are as such. Or alternately, if the relative phase is, if there's a minus sign in the relative phase, then the high intensity is to the left and the atom would move to the left. So the force it feels is dependent on the phase relation between these two beams. Now, the way we're going to actually implement this setup is by placing atoms inside of an optical cavity. So I've drawn the cavity mode. The cavity mode is a sine wave, which has regions where the electric field inside the cavity is positive and other regions where the electric field of this mode would be negative. Now, we place the atoms specifically at nodes of this field. Placed at nodes, they actually nominally would not scatter light into the cavity at all. They're not coupled to the optical cavity when they're illuminated with light that comes in from the side. But should these atoms move in response to some sort of fluctuation, quantum, thermal, I don't know, somebody kicked the instrument, which happens, then they would move into positions where they actually collectively radiate light into the cavity. The light inside of the cavity would carry a phase which depends on where they've been pushed. So if the atoms have all scooted to the right with respect to these nodes, they emit a positive value electric field in the cavity that interferes with the side pump and pushes the atoms further to the right. So now there's two things afoot. There's the tweezers, which are trapping atoms at the nodes. That's one influence on the atom. And the other one is this optomechanical business that pulls the atoms to the right or to the left. And you can ask which of these sort of forcing potentials wins. And that depends on how strongly you pump the atoms or how much light is resonating inside of the cavity. So at low pump strength, the tweezer wins. The atoms are all remain localized at these nodes, or their center of mass degree of freedom remains on average 0. But at high intensity, this optomechanical instability wins, and the atoms, in response to a fluctuation, would actually move irreversibly to the right or to the left. And this is known as the superradiant Dickey phase transition. I'll get back to that a little bit later. But you see, of course, it is a symmetry-breaking phenomenon. The atoms will spontaneously choose to jump to the right or to the left, and then that decision will be reinforced by the optomechanical response. This is not an entirely new topic. So this optomechanical self-organization of atoms in a cavity has been explored previously. There are these very famous experiments by the Esslinger group where they placed a Bose condensate inside of the cavity. They illuminate it just as we do from the side. And above some intensity of light, these Bose condensed atoms self-organize into some kind of density modulation that scatters light into the cavity. And there's a Z2 symmetry breaking in this system where the atoms enhance the density either at the filled in or the empty circles within this checkerboard pattern. And correspondingly, they scatter either positive or negative valued electric field into the cavity. We're returning to the same Dickey model experiment, But instead of working with a system of, let's say, 10 to the 5 atoms, we're working with a system of like 10 atoms, and we're deliberately placing them at locations right between these two choices. So very much, just like I explained earlier, the atoms will all self-organize either by moving onto the even sites or the odd sites of this particular lattice, but only with a one-dimensional system at present. Okay, so we do these experiments. For technical reasons, the atoms are actually placed at half-integer wavelength spacings away from one another in this one-dimensional lattice. But in any case, we expose them to light, and we look at the electric field of the cavity by looking at the emitted light with a heterodyne receiver. The electric field in the cavity, of course, has a complex value. And here's the plot of, let's say, the two quadratures of that complex value. And for a particular system realization having to do with what is the phase of this light that's driving the atoms, we'll see that the cavity field shows a dominant signal along one particular quadrature. So if I just take the value of the electric field along that direction, that's now a scalar quantity, or a scalar quantity and a real one. So I'll just plot it here. So this is the projection of the cavity field along this axis as a function of time. This is data we get from one run of the experiment, and in this run of the experiment, we've ramped up the pump field and then left it on. So what do we see? In this particular run, the atoms broke symmetry spontaneously. The atoms all decided to jump, let's say, to the right and emitted a positive valued electric field, and you can see that there's a value of the electric field definitely away from 0. But a little bit thereafter, they change their minds and they decide they'd rather actually be leftists. So they move over to the left and now they emit a negative valued electric field. Okay, so we're going to characterize these trajectories on the next slide by taking short time bins of this data stream. So that gives me a lot of samples from each run of the experiment. And then we're also going to run the experiment very many times. So we're going to get a large ensemble of measurements and altogether plot the distribution of the electric field that I obtain from this experiment. And when we do so, we see the phase transition that we expected. At low pump strength, the system remains in the unbroken symmetry state. At high pump strength, there's a broken symmetry, and the electric field coming out of the cavity is either large and positive valued or large and negative valued. All right, now there's three things I want to tell you about the measurements that we've made on our system. The first is that we can determine the critical point at which this phase transition, this bifurcation occurs. And we can do so by looking at these histograms. I told you we have a lot of data from single runs and from the ensemble of runs. So here's a histogram of all the measurements under a particular measurement condition. And below the phase transition, you see this histogram is unimodal and centered at 0. And above the phase transition, the histogram becomes bimodal, showing this bifurcation of the system. And the point at which we go from unimodal to bimodal can be very nicely captured by fitting these histograms to this sort of empirical probability distribution function, which looks like a Boltzmann distribution for considering the free energy of the system. And when this parameter capital B, which you can think is related to this free energy parameter B divided by the temperature, but anyhow, this capital B, when it flips sign, that marks the distinction from unimodal to bimodal. And I can just plot that as a function of the drive strength, and we see that the phase transition occurs at a particular strength of the drive field. We can see also that the phase transition point varies with the number of atoms in our system, so it varies with system size in a way that is, fairly close to what we would have predicted. We would have, from the mechanics of the system, we would expect the critical point goes like 1 over the square root of number of particles in the system. That's roughly the scaling that we observe. The discrepancy between this band and our data has to do with our not really understanding what is the temperature of the atoms inside this particular setup. Anyhow, we can measure the critical pump strength quite clearly. The second thing I want to bring up is the following. There are theorists in the room, is that correct? Yeah, great. Okay, so for my theory friends, I hear the following statement often, that phase transitions occur strictly only in the thermodynamic limit. And that is true, but it maybe should be amended to the following statement, that phase transitions occur or persist forever only in the thermodynamic limit. That is to say, whenever you're asking whether or not a phase transition has occurred, you must specify a time over which you consider that the broken symmetry state persists. You can say, has a phase transition occurred with respect to a 1 second measurement timescale, or a 1 microsecond, or an age of the universe? And you'll get different answers to the critical points and to the specifics of the phase diagram depending on this time. Because after all, there are no thermodynamic, n equals infinity system. Every system is finite size, right? Even a bar magnet only contains a certain number of particles. And if we wait a very, very long time, even a ferromagnet will flip its orientation. It might take many universe lifetimes, but it will happen eventually. So that statement is emphasized by looking at our data again and looking at those distributions again, those histograms, and again finding the critical point, but measuring not for short periods of time, let's say 5 microsecond time bins, but actually taking longer time bins and trying to see, has my system decided to adopt a symmetry broken state for not 5 microseconds, but let's say 50 microseconds. And if it's 50 microseconds, then actually the critical point moves. And we see for our mesoscopic systems that the critical point moves a lot. For more macroscopic systems, the critical point moves little. So mesoscopic systems really, you really have to pay attention to this time scale. For macroscopic systems, once you're past a certain phase transition point, the time scale sort of runs off to infinity very rapidly. Okay, I'll get to that a little bit more with respect to the third thing I wanted to tell you about, which is that we can measure the optomechanical susceptibility in our system. And the way we do that in this particular experiment is we first push the atoms away from the nodes inside the cavity. So we put in some explicit symmetry breaking. And then we quench the system, or we drive the system across the phase transition, and we measure what is the average electric field or the average displacement of atoms inside of the cavity. So from the ratio of the initial displacement to the final displacement, we can calculate a susceptibility, and this is the susceptibility as a function of the pump strength for two different numbers of atoms in our system. And I'll point to a couple of features of this graph. One is that the susceptibility does not diverge at the phase transition point. That's to be expected because we have a finite size system. In fact, the susceptibility at the phase transition point should scale with the square root of the number of atoms. A second thing we see, which is maybe a little bit bothersome to some of you, is that in this superradiant phase, or the equivalent of the symmetry broken ferromagnetic phase, we see actually a very large susceptibility. Usually you think about susceptibility being something that just diverges at the phase transition. But I should emphasize this order of operations that we've done here. We've first applied a magnetic field, let's say, and then we've cooled the system across the ferromagnetic phase transition. So in that sense, the large susceptibility makes sense. Okay, let me emphasize that point also with the following. So there's a relation, as you know, between the susceptibility of the system and the fluctuations of the order parameter. I just told you, however, that there's a particular order of operations where we've measured the susceptibility in our system. So in fact, there's two different susceptibilities by which you might characterize a system. One is you might think about a susceptibility like what we've measured, which is where you first explicitly break symmetry in, let's say, the paramagnetic phase, and then you turn up coupling, and you can measure susceptibility under those conditions, just like we did. Or you can do what you might otherwise also do with a ferromagnet, is first, form the ferromagnet, so turn up the coupling, and then apply a little magnetic field and see if it responds. And in the ferromagnetic phase, you get two very different susceptibilities from these two orders of operation. In one of them, as I've tried to argue with you, you get a very large susceptibility in the ferromagnetic regime. And in the other one, you get a very small susceptibility. That's what leads to this susceptibility diverging at the phase transition. So the stuff on the left side of this equation depends on the order of operations. There's some ambiguity. But what about the right side? On the right side of the equation, we can ask a separate question, which is, over what ensemble are we taking this, are we considering these fluctuations? So we can consider what are the temporal fluctuations of the order parameter. Like we run an experiment, we keep a track of the order parameter as a function of time, and we look how much it fluctuates as a function of time. Or we can make many, many magnets and look at all of their magnetizations and collect and characterize the fluctuations from that ensemble. And you therefore can get two different kinds of fluctuations that belong on the right side of this equation as well. In the normal phase, the paramagnetic phase, it turns out it doesn't matter in which way you measure susceptibility, and it doesn't matter which kind of fluctuations you characterize, you get the same answer. But in the symmetry-broken phase, let's say in a ferromagnet, it could matter. In the macroscopic regime, it actually matters a lot. You get two very different answers to the fluctuations and two different values to the susceptibility depending on the order of operations. But for a mesoscopic regime, how should we consider this question? So let me try to describe it as follows. So here's, let's say, a phase diagram going from a normal phase, or if I will, I've always been using the example of magnetism, so like a paramagnet, going from a normal phase to a symmetry-broken phase, like a ferromagnet or the superradiant phase of the model that we're looking at experimentally. Here's the critical point, and I've emphasized to you that in specifying the critical point, I have to tell you with what time scale I'm defining the critical point. All right, so let me put time scale on this graph as well, or if you will, I'm looking at systems in terms of their frequency response, and I can plot the inverse frequency on this axis. Now, every system has some kind of time scale over which it becomes ergodic, over which it actually samples all of the possible states that it can reach. In the paramagnetic phase, that mixing time is small. In the ordered phase, the ferromagnetic phase, that mixing time grows, right? And how rapidly it grows as you move across the phase diagram depends on the size of the system. So for a large-scale ferromagnet, as soon as you pass the critical point, then basically the system is like infinitely decisive. It just breaks symmetry and stays there, and it never mixes up. But for a really small nanomagnet or a mesoscopic system, you would expect this rise to be more gradual. This is like the time over which the system actually ergodically samples all of its states, not just the one broken symmetry state that it fell into to begin with. Now, these kind of separate two regimes. So if you're looking on this side of the phase diagram, and you're looking at short time scales, your system will look like a macroscopic system. So you're looking for time scales that are shorter than the time it takes to mix up. So in these conditions, initial conditions will matter. The order in which you measure the susceptibility will matter, and the answer you get for the fluctuations will depend on whether you're looking at an ensemble of systems or at temporal fluctuations. But if you look over much longer time scales, long enough that the system actually mixes among its broken symmetry phases, then the system looks more like a mesoscopic system. And under these conditions, the two types of susceptibility that you measure would give you the same answer, and the two types of fluctuations you quantify would give you the same result. All right, so let's check this out experimentally. We'll look at our system either over short times or long times, and look at the fluctuations of the order parameter as a function of the coupling strength. So that's shown on this graph, and I'd like to focus you on these two plots here. So for a small system, which is clearly mesoscopic, I can look at this histogram that I talked about previously. I can look at what we get if we look at the temporal fluctuations of the system or the shot-to-shot fluctuations of the system. And you see that as soon as we cross the phase transition, these two values diverge. If we're looking for just averaging over short periods of time, that's because we are pretty soon sampling the system over a time that is short compared to its mixing time. But if we look for longer times, you see that these two types of ensembles track each other for longer, right? Because even though we've passed the critical point as defined by zero mixing time, it takes a while before we've crossed the critical point defined by this long period of time. Okay, so that's what our experiments currently have to say about mesoscopic physics, and we're interested in pursuing this further. All right, with the remaining time, let me tell you about some of the upcoming ideas that we have. One is to enhance the programmability of the system that I just told you about. So in the system that we're studying this far, there's a mapping of our system to the Dickey model. I didn't really emphasize this in my presentation, but the standard Dickey model, or the thing that is maybe was more worked out by Hepp and Lieb, is one where I have a number of spins that couple to a single electromagnetic mode, and the coupling is something like the electric dipole coupling, and every emitter couples identically to the electromagnetic mode. The Hepp-Lieb model has a Z2 symmetry, which is, here's the symmetry operation. And that symmetry is broken in the superradiant phase. The Dickey model is realized experimentally as a driven dissipative model in the manner that I told you about. You drive the system inside of a cavity and you look for the phase that's produced as a response. And the difference between, I just want to emphasize a few differences between studying the Dickey model as an equilibrium system versus a non-equilibrium system. A couple of sort of accountings or bookkeeping differences are that the energy of a photon is now set to be a different value depending on what frequency you drive the system. That is to say, we analyze the system in what's known as the rotating frame. A second practical difference is that the energy of the spin, or the excitation energy of an atom, is now set by some low energy value depending on what two-photon transition you're driving in the atom. But the third point, and this is the most important one, is that in these driven dissipative systems, you're no longer studying an equilibrium phase diagram. You're asking, does my system reach a steady state? And if it reaches a steady state, what is that steady state? Now, in the case of the standard Dickey model and its realizations, just like the one I showed you in the previous number of slides, it turns out the system always does reach a steady state, and we can plot its phase diagram. It looks a lot like the phase diagram of the Dickey model. There's a transition from the normal phase. This is taken from Tillman's data, Tillman's early paper. There's a transition from the normal phase where there's unbroken symmetry, but the system is stable, to the superradiant phase where there is a broken symmetry. The transition is second order, and we understand all of that. Now we'd like to program a more complicated model. So here's like just one example that we've thought about theoretically. What if, since we can optically resolve each of the atoms in our experiment, we just expose each atom to light that has a different optical phase? And we'll make things simple. We'll take our atoms, divide them up into little n bunches, and each one will expose with a phase that just advances stepwise as you go around the unit circle. Okay, so this is the n-phase Dickey model, just a simple extension of the previous model, but using a sequence of complex coupling strengths to the cavity mode. This system turns out to have a richer symmetry, either a Zn or a Z2n symmetry. It turns out depending on the number of blocks that we've built into the system. And now here's what we obtain, at least theoretically, for the phase diagram of this driven dissipative system. So here's the phase diagram. And let me actually first consider a regime that's not on this phase diagram, which is the infinite dispersive limit. So where the detuning from the cavity is very, very large, and we can forget about the fact that the cavity has a finite lifetime in it. In that case, we see what you see in the canonical or the standard Dickey model. There's always a steady state. There's a phase transition from a normal phase to a superradiant phase. The phase transition is second order. There's something interesting about the superradiant phase because it breaks a higher than Z2 symmetry. It breaks this Zn or Z2n symmetry. That's interesting, but there's nothing, dramatically different about the model. But one thing that's very different is if you go away from this limit. So if you consider the fact that there actually is a finite line width of the cavity, and what we find now is something different. First of all, we find that the phase transition from the normal phase, if you will, to the superradiant phase is no longer second order, it's a first order phase transition. And secondly, we find that the normal phase is now always dynamically unstable. So there actually isn't a steady state in the normal phase. There's only a steady state that you find in the superradiant phase. So that's different and interesting. And I won't go through the details of how we describe that theoretically, but I'll just point out that one of the key elements that's different in this system is the presence of non-reciprocal interactions. And this turns out to be what makes the normal phase always unstable in this system. To illustrate how you get non-reciprocal interactions in this driven dissipative system, let me use the following simpler model. So imagine I have two mechanical objects in the cavity, let's say two atoms or two batches of atoms, and I drive some of them with light, and I drive the other one with light that is advanced by a phase of pi over 4, just for this simple illustrative example. Okay? And let's say that the light that's driving this system is not very far away from the cavity resonance. It's close enough to the cavity resonance that the cavity responds a little bit out of phase with the light that the atoms are emitting. Let's say that phase is exactly pi over 4. Just we've picked a particular detuning from resonance. All right, now what happens? So let's say this atom were to move. As before, it would generate light inside of the cavity. The light inside of the cavity is pi over 4 different in phase than the light that's driving that atom because of this nearness to the cavity resonance. This light interferes perfectly with the light that drives the second atom, and that leads to a force on the second atom. So as such, there's a light-mediated force. If this object moves, then it puts a force on this guy as well. But let's consider the opposite situation. Let's say it's this atom that moves. Okay, it populates the cavity with light that is now overall pi over 2 phase shifted with respect to this light. And now there's no longer any interference between these two light beams. There's no generated force on the second atom, and there's no communicated interaction. So we now have a perfectly non-reciprocal phonon transfer from one atom to another. And that turns out to be the origin of this non-reciprocity. All right, so now in terms of sort of a few more technical updates, how much time do I have? Minus, okay. Well, I'll keep running up my debt. It's an American thing. Okay, a few things I want to tell you about. One is we've made some advances in making mid-circuit measurements. So I just told you about how we characterize our atom optical system entirely by looking at the light coming out of the cavity. I'd also like to be able to see the atoms inside the cavity and figure out what they're doing as well. And a way we've recently implemented that is actually turns out to have been previously done just recently by Vladan Vuletic's group at MIT. But basically the idea is we have all our atoms inside of the cavity, but we want just one atom to talk to the cavity, even though all the atoms are located in the cavity. And the way we achieve that is by exposing the atoms to light that is near an excited state transition of the atom. And that shifts the excited state energy by a large amount so that the atom can be either tuned in or tuned out of resonance with the optical cavity and with light that is driving the atom. So in that sense, we can selectively couple one or a few atoms to the cavity and then hide all the other atoms so they don't have any optical response. It turns out that this tune out is a little bit easier for us to achieve. So the way in which a mid-circuit measurement would be realized is that in this register of qubits, when I want to measure just the state of this qubit, I shift all these other guys way out of resonance. I expose these atoms to light, which fluoresces into the cavity, and I collect the light inside of the cavity. So we've realized a mid-circuit measurement using this technique, and here's what can go wrong. It could be that while we're measuring this atom, atom A, let's say some other atom, another qubit in the cavity scatters light, like picks up light that's scattering the cavity and then scatters it out somewhere else. That would end up collapsing the state of the second atom because we would know in what state it is. It's in the state that scatters light. So this would be like a certain crosstalk error that leads to coherence loss. There's also a phase shift that the atom can acquire. There's an energy shift of the other qubits due to light that is scattering in the cavity from this first qubit. That would also lead to some kind of crosstalk, although that is perhaps a fixable problem. So we've realized a simple mid-circuit measurement experiment where we have a register of just 2 atoms, and our job is to run a simple quantum circuit, so just a Ramsey sequence, measure the state of one of the atoms, and then see whether we bother the state of the second atom by looking at its coherence. And, okay, so let me just tell you the upshot. The upshot is single atom detection in the cavity is actually highly efficient. We know that already. We can measure the state of a single atom within about 40 microseconds with measurement infidelities that are below 1%. But the good news is that we find that now checking on the coherence of a second atom, we find that its coherence is really not affected by the measurement. So with not really great measurement specs yet, we know that if we hide the second atom by shifting its energy by about 800 megahertz, we see no influence on the contrast of the Ramsey fringe or on the phase of the Ramsey fringe. All right. A second thing I'd like to tell you about is that we're starting to drive Rydberg excitations on atoms trapped in our optical cavity. I won't go through the details, but the kind of idea is that ultimately we'd like to operate something like a very coherent Rydberg quantum computer inside of a cavity, and have the cavity be a measurement device or a transduction device, but not have the cavity itself be what's responsible for the interactions between the atoms, because optical interactions are kind of nice, but they're also pretty lossy. So we've been playing around with Rydberg excitations in our system, driving rubidium atoms through a 2-photon excitation up to a Rydberg level. We're able to see the excitation to a Rydberg state by looking at whether an atom is lost from a trap. It was at first not really clear whether this was going to work out in our system because we have a lot of structure that's not so far away from the atoms. There's the possibility of a lot of electric field from stray charges. That would be problematic. We also have these things called piezoelectrics, which move the cavity mirrors around, and that could generate very large electric fields. So this could be a really terrible place to drive Rydberg excitations. But the good news is that we are able to drive the Rydberg transition once we've learned which wire leads to which part of our piezoelectric. We can actually apply kind of large drive voltages to the piezos. And then when we expose the system to ultraviolet light, it seems like we kind of clean out some of the stray charges that were leading to large electric fields on our atoms. So I think we're pretty far along to being able to drive Rydberg gates on atoms inside of our optical cavity, and that'll make the system a lot more interesting. The last thing I would have wanted to tell you, but should I stop? We should wrap up. Okay, so we're playing around also with ideas for how to displace atoms in tweezer arrays rapidly, and also how to move tweezed atoms not just in 2 dimensions, but also in 3 dimensions, with the idea that now you can start building up perhaps like a 3-dimensional quantum computer architecture, not just a 2-dimensional architecture. And anyhow, we have a paper about this. It involves using multiple acousto-optical deflectors, sort of one in sequence to the other, and we can drive atoms around on really crazy trajectories. Here's a whole tweezer array that's being kind of jiggled around in some weird 3-dimensional trajectory. Here's actually experimental data that shows that we actually did that on our experimental setup. But I don't have time to tell you about it. It's rather technical results. So let me just wrap up. This has mostly been the work of the E6 team, which is my atoms in cavity experiment. Other folks in my research group are working on laser cooling titanium. We've laser cooled all 5 of its isotopes. I can tell you about that. We've also been building up the capability to put ultra-cold fermions inside of Kagome lattices, which I know is of interest to some of you, but I'll not talk about that. Thanks. Sorry for going over.
So we have time for a few questions. So,
Yeah.
Hi, thanks for this great talk. I have a question about the first part, about the phase transitions within a mesoscopic system. I was wondering, in this case, could you actually see a CAD state of these two superradiance phase?
Yeah, right. So it's appealing that in particular in these more mesoscopic systems, you might, as you break symmetry, actually remain in the unbroken symmetry state and just be in a superposition of a magnet pointing right and left.
Yeah.
But this is remember, this is an open quantum system. It's constantly shedding information about what's going on the inside, right? So as soon as there's enough light coming out of the system to collapse, to provide information about whether the system has broken to the right or to the left, then that superposition should die.
They won't be able to somehow cancel each other at the readout part, such that you don't effectively gain any information?
That I'm not sure about. Maybe, but I kind of doubt that.
That would be cool. You kind of have a superposition of different center of mass, kind of, right?
Yeah, yeah. So I do think that an ever higher cooperativity cavity we should be able to kind of hide that information longer and reach sort of ever larger CAF states, right? I mean, obviously, if the system is just broken a little bit to the right or the left, then actually you need a lot of photons to know which side you're on. So there is the ability to maintain a coherent superposition of right and left to some extent, and the extent to which you can maintain it probably has to do with how many particles we have and what is the cooperativity of the cavity. There's another kind of quantum eraser kind of approach that I can imagine where you drive the system that generates light inside of the cavity, and then you drive the system with an opposite phase that actually pulls the light back out of the cavity in a way that you can have displaced the atoms to both the right and the left without actually leaving a trace.
Right.
So those might be things we would think about.
Thanks.
Yeah.
Hi. Thanks for a very nice talk. I have a quick question about the mid-circuit measurement part.
Yeah.
So I just want to get some sense of the time scale. So within the coherence time of the whole experiment, like how many layers of the measurement can you do? For instance, if I want to engineer some circuit.
Right, right. So actually for neutral atoms, the coherence time is very long. So we're talking about, let's say, coherence in the hyperfine states of an alkali atom or something. Even in an optical tweezer, that can be very long, certainly many seconds, probably longer if we work at it. So in that sense, if a mid-circuit measurement takes, 40 microseconds, then actually there's plenty of time for lots and lots of stuff to happen. What's interesting is also that 40 microseconds is within the lifetime of a Rydberg atom, too. So you could even think about mid-circuit corrections to Rydberg qubits, or to gates that include the Rydberg excitation. So that's an interesting new regime for us to think about.
Okay, so just get some numbers out. Can I think of it like I can have 50, 100 layers of the measurement before the whole system decoheres for like Rydberg atoms?
Okay. Well, you should ask the guy sitting right next to you on his computer. But the coherence time is really quite long.
Okay.
I don't think that's so much the limit. As I understand, the limit is the gates are a little bit crappy. So there's maybe 0.5% or so error in the 2-qubit gates, and that can be, not so there. Yeah. So there's errors in the gates. Uncorrected, you're going to be able to get away with maybe 50 to 100 gates or something like that. Gate layers before the coherence is really gone. But now that one is past the error correction threshold, now we're talking about a totally different game. Yeah,
I see. Thanks.
Yeah.
I'm not sure if there's still time, but I was just wondering, you had some discrepancy in your experimental data to the theory in the optomechanical superradiance part.
Yeah.
Especially in the critical point. I was wondering, did you take into account the longitudinal motion of the atoms in the tweezer?
Yeah, I think the discrepancy is mostly theorists.
So you did not take
No, I'm just kidding you. Yeah, we did consider the three-dimensional motion of the atoms and how the three-dimensional motion in the tweezers would influence the position of the phase transition point. That's actually that's why there's that band of possibilities that I showed on that graph. That has to do with what we state the initial temperature is. So the data are, parallel to that band, but at a little bit even higher temperature than we think the system is at. But this is like a driven system. The atoms are scattering light all the time. Who's to say that they're characterized by a single temperature? I think that's probably the source of what's going on.
Thanks.
Yeah, let's do one more question.
One quick question. So, is there any anything that determines the time scale of those oscillations? You show the oscillating phase of the. If you look at long time scales in the symmetry breaking.
Yeah, right. This was a little bit related also to Roderick's talk about symmetry rebreaking, right? Where the hell are we? These things, yeah.
So
okay,
why that specific?
Yeah, so anyway, that was a lot of tick, tick, tick just to be able to say, I don't know. So yeah, we see kind of a zoology of trajectories. We haven't spent a ton of time analyzing them yet. We sometimes see that the system breaks symmetry and it's happy, just kind of chills out there. We often see like this dynamic where it seems like it cools and then it kind of gets heated out of that and then it kind of jumps over. We're not sure if that's really like a Poisson process or if there's some delay. And then sometimes we see these actually but rarely, maybe a few % of the time, these rapid oscillations. And you can think of it a little bit like there's a mean field energy, which is now, a double well kind of potential. And sometimes we catch, when we drive the system, it happens to have a lot of energy, and it just zips back and forth over the top of that barrier. Other times we run it, and in that particular instance, maybe it has little energy, so it falls into one of the wells. Maybe that's the way of understanding it. But there's a lot of data, there's a lot of dynamical data in the experiment, and we're in the process of learning about it. So for example, this sort of trying to check on the connection between these susceptibilities that we observe and these fluctuations that we characterize. This is obviously going in the direction of like testing the fluctuation dissipation theorem and seeing whether the constant relation between the susceptibility at some frequency and the fluctuations of that frequency, whether that holds. And at thermal equilibrium, it does, but we have a driven dissipative and quantum mechanical system, and I don't know what to do with the fluctuation dissipation theorem under those circumstances. So we should experimentally test it.
Can I ask like one super quick question? So in the mid-circuit measurement, you showed like a Ramsey fringe, but did you use the cavity to do those measurements? Because it seems that the fidelity was not, like the contrast was not like 99%. So I want to make sure that I understand it. Like you're measuring an atom state or if the atom is there or not.
Yeah, so we're not doing a great job at state preparation at this point. This is the qubit is encoded in the m=0 states of the 1 and 2 levels of rubidium. And at this point, we haven't put a lot of energy into making that state preparation very reliable. That's largely what is influencing this. The second both measurements are made using the cavity as the measurement instrument. But given that the infidelity of the measurement is sub%, that's probably not influencing these data.
So those is basically spam corrections, effectively, like state preparation. Basically.
These are probably state preparation and not so much measurement. It's more state preparation error.
I see. Okay.
Yes.
Okay, let's thank Dan and all the morning speakers. We meet again.